Hi, ladies and gentlemen. Good morning, good afternoon, good evening from wherever you're joining us for this special webinar that it's on a Monday evening our time in Singapore right now. So my name is Thean Ho, and together with SpenglerFox, we are hosting this webinar to address some of the technology challenges and opportunities facing semiconductors in the years to come. And I'm just going to quickly go through some of the objectives of this webinar. And essentially, we have over 50 participants joining us, including 5 panelists and moderators, to address some of those questions or challenges that faces our industry. And essentially, this is going to be a 6-monthly event, and we hope to gather a community of thought leaders that we can really build up an active forum. And moving forward, I would like to introduce Lighthouse and SpenglerFox. Lighthouse is a partner and affiliate of SpenglerFox, which is a leading executive search firm in 45 locations with over 250 consultants around the world, right? Most of us come from the semiconductors background, and we are the trusted advisors to some of our partners. And we are present in most of the geographies that our partners need us to be. And essentially, we provide customized talent solutions. And here are some of our key clients around the world. Some of the participants in this webinar will be from some of these partners. And essentially, these are some of the key clients that we work with in terms of senior executive search and business consulting solutions in various regions, right? And right now, the format of this webinar will be going through some of these key topics by various leaders in our industry, and some of them come from research institutes, some of them come from fabless IDMs, and some of them are leading memory development for emerging memory. So very quickly, I will go through the panelists, but before I introduce the panelists, some of the ground rules is that all the audio and chat with participants are deactivated. If you've got any questions to ask, please click on that Q&A button at the bottom of your screen, and we will address it when the moderator finds the right and relevant time for it. So without much further ado, let me introduce the moderator and the panelists. So Prof. Thean is our moderator for this webinar, and he's the Dean of Engineering in NUS. He came from a very rich background with IBM, Freescale, Qualcomm, iMac, and right now he's heading up the entire Faculty of Engineering in NUS in Singapore. And next we have Dr. Lowers. He's been a legend in iMac. He's right now running business development. And previously, he was doing a lot of research programs. He was with Transwitch, and actually, I think he started his career in IMAX as well. Next, we have Kelvin. I'm sorry, Kelvin. Kelvin has been with Foundry, Fabless. I mean, he's been with Samsung, ARM, and right now he's running Semi5 in the US. So he comes from a very diverse both research and commercial background within semiconductors as well. Last but not least, we have Dr. Huai. Dr. Huai is really a leader in emerging memory. He was a co-founder of Grandis, and even before that, he was with Western Digital. And right now, he's the EVP of technology with Avalanche Technology. For those who are familiar with MRAM or any kind of emerging memory, Dr. Huai is the go-to person. So right now, we have gone through the panelists some of these topics that are going to be covered. I think Prof. Thean will be covering some of the key things that is being addressed that Moore's law is going to break. And I think without much further ado, I'll hand over the time to Prof. Thean on his thoughts on whether the size really matters.
Thanks, Tian Ho. So I thought, first I would thank Tian Ho and of course everyone for inviting me here to moderate the panel. I'm very happy to have together with me my colleagues and ex-colleagues who have been working on this topic. So here are some of my thoughts. Does size matters and what else? So it's a very informal sharing. So next, please. So, one of the questions that's asked every 2 years is, when's Moore's law going to end? So I think it's a very interesting question, but the funny thing is that we keep asking it, right? So here's one slide I want to show, what actually happened. So back in 2002, people predicted Moore's law is over because gate dielectric no longer scales. And then, basically about 8 years later in 2010, after 90 nanometers, of course, we get to 22 nanometers. And there again, the experts are saying no more chip performance scaling, and Moore's law is dead again. And then computer architecture now takes over. So we come to 2 years before this year, that 2018, and again the Moore's law is dead again, right? In the sense that basically that's as many transistors we can make. We no longer can design chips like we used to. We have to be more creative, and that's when we're talking about 10 and 7 nanometers. And now today in 2020, okay, so we just got our 5 nanometer technology. We saw the A14 Bionic chip, which is Apple's 5 nanometer chip. So every 2 years or more, we prove ourselves wrong by asking this question. So what are the right questions to ask? Actually, it's starting to make us look foolish. So let's next. There are 2 questions to ask. Okay, so one of them is really a big topic for this panel. Is does size matter? And my thoughts are that it's not, size do matter, but it's not what we think it is. Okay. The second question is chip scaling all about just Moore's law? And what I'm trying to purport is not necessarily so. Okay, next please. So size matters, and what kind of size and what we talking about. So one of the first thing is size of the market. So size of the market does matter. In fact, there is a great demand for electronics, and with a great demand for electronics, there's a great demand for semiconductor and a great demand for chips. So new applications like AI, 5G, IoT all require advancement in chips. Okay, next. Now the size of the fab matters. So if you're going to go address some of the most advanced technology at the bleeding edge, you need to be able to invest in huge fab. Here's one slide that shows the sort of the fab investment throughout the years as we move through technology, right? You can see today a gigafab for 5 nanometer production is somewhere in the $17 billion and beyond, right? So and such facility needs to not only contain very high value capex investment, but they need to be able to produce chips at high throughput and high yield. Next, please. Now, so size of the tool matter, and the size of what you print matters. So actually in recent years that we see in all this leading edge technology, the cost of lithography actually dominates everything. And lithography is really one of the fundamental foundations of allowing us to get to the smaller and smaller sizes. So as you print smaller and smaller features, your tools get bigger and bigger. So in this case, for instance, the ASML's extreme UV tool, right? It's almost the size of a bus, actually, just to be able to print features down to 10, 12 nanometers with a single print. Okay, so next. Now size of, now we come down to the devices, right, on the chip. Now, what's surprising is that actually size of wires matters more than the size of transistors. So we always talk about scaling transistors, but actually for every transistor, there are at least 3 to 4 wires connected to it. And the size of wires, the scaling of the interconnect actually matters a lot more. In fact, most of the innovation today in patterning are to address wires. How do you print them? And how do you layer them, right? So next. So to cap off this particular slide, the demand and opportunity continue to drive the business. And the size of that business, the size of the opportunity pushes the technology forward in terms of investment and innovation. Okay, next slide. Now, with the new application comes new problems. Okay, so here's one cheeky slide that I got from the MIT Technology Review, right? It says that training a single AI model can emit as much carbon as 5 cars in their lifetimes. So doing so-called advanced computing doesn't mean that it's energy efficient. In fact, deep learning AI actually uses a lot of energy. So if you click on that again, you can see here this is a comparison compared to even car emission. A data center running advanced AI learning algorithm can actually consume a lot more energy. So there's nothing to do with being green when you go to advanced computing. Next slide, please. So here's what some of my folks here at NUS are working on. So to address this energy concern, one of the problems to solve is memory access energy, right? So if you do look at data abundant computation, you really need to bring the memory and the logic much closer together. Next slide. So here are two images that I actually took one from a paper by Wei Liu and one from Philip Wong and Subhashish Mitra of Stanford, right? Here it says that actually the energy required to access data, shuttling data between logic and memory, will soon dominate most of the energy expense on a chip. So we really need to address that, right? And that's where the innovation in terms of memory as well as computer architecture will come from. Next slide, please. So there are ways to bring memory and logic closer together. One of the ways is to be able to build the memory directly on top of logic. And you can see that now. MRAM technology does that. And I think more and more for embedded memory processing, you need to find innovations of how to bring the memory closer and closer in terms of access to the compute unit. Next slide, please. But there's a few issues, right? When you start building stuff on top of interconnect just don't like heat, especially copper. So nothing can be processed above 400 degrees C unless you want to fry, the wires and allow the copper to leak out of the enclosures, right? So new innovations in materials will come, and they will be able to address basically how to add functionality on top of layers and layers of interconnect. And that means the research in terms of materials for chips will move towards low temperature or low thermal budget processing. Okay, next slide, please. So some of the things that, for instance, that we're looking at is, what about these new materials called 2D materials, for instance? These are materials that naturally form, that could have interesting function, but they are processed at low temperature, and they can be transferred to the back end of chips. So instead of building the chips all at the bottom, the functionality, now start building them on top of interconnects, and then add functionality in the third dimension. Next slide, please. So many opportunities, and then some of the panelists will talk a lot about this. When you start building circuits in 3D and build up memory and logic coming closer together, you can have very interesting operations and data processing architecture. Right? For instance, 3D in memory computing, for instance, which I don't have time to get into. All right, next slide. So to come back to the point, which is, how's Moore's law continue to beat expectations so far? So I believe that there are 3 points. One, chip scaling is not traditional Moore's law. So some people say Moore's law is dead, back in 45 nanometers. Maybe so, but we are still scaling the chip. Size do matters, and I think the size of many things, but one of the most important things is the application. As long as there's a demand, there will need to be a supply. And I think, for universities and research institute, I think the new research direction will be looking at systems and material co-innovation. How do you bring these two together to get new innovation? But that's it for me. Thank you.
Thanks, Prof. Thean.
Because
So all participants are, if there are any questions, we'll be addressing at the end of all the presentations, right? So, but please feel free to click on the Q&A button. We will poll all these questions at the end of all presentations, right? So without much further ado, we'll hand over the time to Dr. Lauwers in Belgium.
Hi, hello everyone. So I thought to give a few slides, a perspective on how we see the challenges in the next years and where this size element comes in, or it doesn't, or how things are changing along the years in front of us. But you will see that size is everywhere present somehow. Next. So actually, this is just as introduction, has been tracked like number of transistors over the decades. And you see it has been consistently increasing exponentially in systems, right? So in that sense, there is transistor density scaling is continuing and is planning to continue. However, when you would look at performance, and you plot it off versus like a single thread performance, then you see it's somehow saturating. So we cannot claim that there is no change in the future compared to the decades behind us. It's like, how do we address that? Because of course there is a lot of performance at system layer, at architecture layer as well. Next. So actually, I brought three angles together. The vision is definitely for the future, highly integrated future 3D system, and where you have a lot of innovations, EDA, cooling, of course, chip scaling, but definitely also interconnect breakthroughs. This complete heterogeneous integration is like our driving picture for the next decades. Now, underneath, what you see is this understanding of roadmap at the right, where compute PPAC, if you plot it out node to node in the next years, you cannot have like the 50% improvement or every time. It's impossible. So we compensate that for a number of years already via design technology co-optimization, looking at libraries, what can you do at design level. But on top, like the next years, we will need to do the next step there, like to have also system technology co-optimization in order to meet up with that improvement, like node over node. And to the right-hand side, to the left-hand side, you see, regardless of that, like we say, it's system technology, still the improvements will be at the technology level. That's what we believe. Like the knobs are in the bottom. Like the knobs will be in material, will be in pitches you can make, in like bonding pitches, in like how you make thin film transistors in a highly scaled device. So it's like the knob, like the high-NA litho. It's like how dense you can print. That will finally enable your system. It's like the paradox, like you need to look higher up for the system, but the knobs are at the bottom. Next. So this is just as an example, our current view of logic roadmap, and many of you have possibly seen versions of that in presentations. This is a recent one where we plot out, of course, you see nanometers, one thing, of course, not so many physical dimensions relate to these node numbers, but we can forecast nodes like 2 nanometer, 1.5 nanometer, 1 nanometer, and beyond. We put the pitch numbers there, but these are, I make assumptions, it's like driving goals that if we want to realize these pitch scaling numbers, look at a 1 nanometer layer, you will need to have serious improvements both at the device level and at the interconnect level. So at device level, we are seeing this trend from FinFET to nanosheets to fork sheets. And then we see this happening further by bringing in the CFET, where you have N and P on top of each other. And the next one is then behind that, the CFET with 2D materials, so atomic channels. So we think the 2D material is one of the key enabling breakthroughs in order to have a further scaling for the next decade. Of course, not only the front end, not only device, there will be a lot of interconnect, and as Professor Thean was saying, it's even challenging there, like at the interconnect, also at the layer of which metals you can use, how you will be able to print it. And also like using the backside, using tricks like the buried power rail and backside power distribution networks. All this together will bring this future scaling. Next. So this is just an example, like on top of that, there is the real 3D integration where you will bring dies together and via various techniques. And we are plotting the work we're doing versus the state of the art. And also there, again, size comes in. You will need to go for aggressive pitches, both for die-to-wafer techniques, die-to-silicon hybrid bonding techniques, but also wafer-to-wafer bonding. So we are talking today like die-to-wafer, 7-micron pitch layer things, right? Wafer-to-wafer, even below the 1 micron, 7 nanometer and going lower. So all these things will fundamentally improve the system interconnect from die to die and enabling, again, further scaling of our systems. Next. As I said, the bottoms, the knobs are in the bottom. So I just took 2 examples of, there are many examples and things we can do, but I took 2. Like one is, we just mentioned already, the 2D materials. 2D materials where it's really, we believe, a breakthrough innovation that will be required. It's not yet there. We are thinking on it. We have R&D work, but it's not yet there in terms of being able to implement it in industry. Like to go for ultra thin and highly scaled gate lengths. So high mobility channels. And then we think these 2D materials can come in. Of course, there's a lot of challenges like how to deposit them and how to realize theoretical mobility also in reality in the device. The right-hand side, there is IGZO, the material, and Professor Thean was hinting also to like the large band gap, low leakage devices. They can also be deposited at low temperatures. So the idea is, can you make smart transistors, for instance, in the back end, or use this like with a low temperature processing budget and enabling like potentially new memory devices and so on. So this for the IGZO. So again, a lot of material innovation will be required in the next decades in order to be able to continue the roadmap and the size scaling. Next. At the system layer, I just want to give one example where we were saying system technology co-optimization. For instance, machine learning. We will have not a one-size-fits-all technology and solution. We might be going to hardware-enabled, optimized architectures for certain applications. Like, for instance, a hardware-enabled accelerator, an accelerator for machine learning. And in that case, like an example we're working on, like for analog compute in memory, where we believe you can really have orders of magnitude efficiency improvement. Like if you have these lines are, depending when you increase the power, you will have higher performance, but by shifting the line, you improve efficiency. So we believe when you go to the edge for highly efficient devices for machine learning, you may be benefiting from these accelerators. And that's where, for instance, advanced memory devices can come in combined with these improved architectures. Next. So the last slide is also an important one. It's simplified, but it's important one. I took it from, I wrote inspired by I Make Data, right? So the requirements and challenges are huge, but size also comes in at the scale of how to do the work and the budgetary level, because it's a challenge. Who will, for this amount of work that's ahead of us, who will be funding the far out work where you have more consolidation and longer ranges in order to do the work, like the high NA EUV or this 2D materials breakthrough. So this is where we think, okay, global collaboration will definitely be required. Two curves there just to illustrate. We expect, like, at the investment level, with investments, I mean tools. We expect, like, if you depreciate that over per year, you will be increasing definitely over 10 years of 50% increase in what you need year by year to invest. That's not easy to do in an R&D environment, but still this is required because tools become more expensive. You need to have more materials to investigate and so on. Second is like the overall R&D budgets, and that's a little bit, I took the liberty to make my own forecast because I'm already 15 years in this type of numbers, where I took some actuals and put them in perspective and see even modest predictions. We may need doubling of the R&D budgets for over the next 5 years. So how to do that, or a 50 to 70% increase, how to do that? So again, probably we need a lot of smart collaboration in order to do that. So that's where also another element of size comes in. Well, that's my intro here. Thanks.
Thank you, Dr. Lars. Oh, that was really very insightful. I think we would love to hear more from you, but because of time constraint, we really need to move on to Kelvin. Kelvin is going to give us quite some insight on custom silicon and how that addresses some of the challenges in the market. And Kelvin, you're up next.
Okay, thanks, Tin Ho. Well, I'm going to save the team some time on size. I only have 2 slides, right? Okay, so very similar view, and actually I'm very encouraged that the research consortium and also the academic part of the industry is looking at very similar challenges, right? Looking at not more store being dead, maybe more store being slowing down drastically, right? So again, similar view from a product perspective. At the end of the day, technologies that we develop and research in the lab, it will have to go to the fab, and then eventually it will have to be used and deployed in designs and hence products for all of us, for the benefit of all of us, right? It is true that we are seeing a slowdown in extraction of PPA, as Dr. Lawes mentioned and Professor Thean mentioned, right? For power performance area. The other 2 important alphabets to remember is also PPA C, cost, and S in terms of schedule, right? We all want to introduce products at on a timely basis. That's also very important in a very competitive world, right? So if you tap next, just one animation there. Although I think it's recognized that the traditional scaling is slowing down, many companies are still trying to squeeze PPA out of technology scaling, right? Try to drive applications from, let's say, 28 down to 16, 14, and then down to 10, down to 7, down to 5, and then goes down from there. We are also seeing a new trend, right? From a deployment from a way of chips on how chips are designed. If you can tap again. there is a evident increase in custom silicon. What we mean here by custom silicon is there are still a lot of ASSPs being designed. ASSP are standard products that the end OEMs or system company procure from the, let's say, fabless companies. But there's also an evident increased trend of companies designing their own chips, right? Whether they do this entirely by internal design teams or by enlisting help from design services companies, right? So I'm showing you three examples here, right? Professor Thean actually mentioned the Apple A14 Bionic chip on 5 nanometer, and all of us probably have read the huge announcement from Apple on the M1 chip, right? This is probably going to set a new trend, right? With CPU, GPU, and multiple functions being embedded on a single SoC. There's also a mention of how memory, a unified memory, I would say architecture being included in this chip. So we can discuss that topic maybe in a panel shortly. That's on the consumer mobile world. In the cloud, data center, high performance compute, some of you may have read about the AWS deployment of what they call Graviton SoC. That's on 7 nanometer. Again, a custom chip, slowly replacing merchant chips in their products, right? And in the automotive space, Tesla also developed what they call a fully self-driving chip. Developed on 14 nanometer, right? And we expect this trend to continue. So just showing you very quickly 3 different products, but there are many more that are being designed today using a custom SoC approach. So this is one angle that is, I would say, slightly different from, let's say, feature scaling, material research advancements, and also new device architecture, right? Designs are being done differently to continue the pace of innovation. Yeah. Next slide. So another angle, and I also am happy to see that there's also a lot of research and a lot of progress being made in the heterogeneous or 3D packaging area. Just to share some examples, graphic on the left-hand side, which I sourced from Synopsys, right? Showing how, for example, one can scale the SoC, introducing different product SKUs, right? 2 CPUs, for example, for a low-end user, 4 CPUs for mid-end, maybe 8 CPUs, for example, for a high-end application, right? So this can apply in a product space where you have different processor and accelerators. And still focusing on the graphic on the left, you can also split, let's say, very large designs. We have seen how some designs can actually exceed a reticle size of 800 millimeter squared, right? So you can split it into 2 dies. They can give you cost advantage, yield advantage, for example. And then certain system designers can also look at how to, I would say, enable different functions on different technology nodes, right? Integrating, for example, logic using certain technology, and then RF and maybe analog on different technologies, right? At their respective cost optimized nodes. And then we also see, for time to market reasons, certain logic products, for example, switch and server chips, tend to go very fast into the next nodes, 5 nanometer today. However, for very high speed interface, high speed SerDes, for example, 112 gigabit or even beyond that, it is very hard to design into this very new node. So they tend to stay at the N-1 node. So one can actually integrate both, let's say, a switch design for logic and partition the I/O out, and then basically combining them on a 2.5D or 3D solution. So the other angle that we see that can give you opportunity is basically what we call platform approach. And yes, size does matter. I think for many designers, we also struggle not only with design costs, right? The initial cost is actually design NRE. There's also a huge investment in IP, for example, typically around 40% of a new design. And fab cost, which translates into silicon costs, right? Whether it's prototyping on MPW or initial prototype runs, right? So there are ways that we can actually reduce this, let's say, from a 1x to just down to 0.1 to 0.3x. Keyword here is how do we reuse and how do we have a innovative, let's say, business model that can help reduce the barrier, reduce the cost barrier to allow a lot more companies to enjoy the technology while realizing their product innovation, right? Again, I won't go through a lot of details. Happy to speak to all of you maybe offline, but these are the, I would say, opportunities for us to continue to realize innovation while we allow the academia and the research institutes, right, to continue to scale Moore's Law. Okay, that is my short intro.
Thank you, Kelvin. And last but not least, we have Dr. Huai, who's going to address on emerging memory and the market it addresses and some of the opportunities and the challenges that we face. Dr. Huai.
Dr. Huai, please unmute yourself. We can't hear you.
Hello, everyone. You can hear me now?
Yes,
hello?
Yes, we can hear you.
Okay.
Yes, we can
hear
you.
I would like to first thank Lighthouse, particularly Thean for inviting me to this exciting webinar to share my perspective on the future memory with you. Next, please. Let's start by reviewing current memory hierarchy and from bottom large latency NAND to working DRAM to top faster cache SRAM. Also are listed here most popular emerging NVM technology along with advanced incumbent memory solution to address memory gaps, enhance performance capacity, as well to meet new application needs. There was a big memory war between NAND and DRAM in terms of latency and capacity. NAND's latency of microsecond compared with 10 nanosecond of DRAM, but DRAM is expensive, has much lower density and capacity. This huge gap has been filled in 2015 by a new class NVM technology named 3D XPoint, developed jointly by Intel and Micron. This new storage class memory is based on the PC RAM plus a novel selector in stackable cross-point architecture. 3D XPoint provides 100 gigabit density with 100 nanosecond latency, and 3D cross-point structure with STT-MRAM and RRAM are also pursued with a new selector to be developed for further improving storage class memory latency and extend operation temperature up to more than 100 to 125 degrees. On the other hand, cache memory SRAM is also facing scaling challenges with significant large footprint. For example, more than 500 F² at 7 nanometer, which limits high capacity plus additional high leakage current in standby mode, a critical concern for low power application. At this end, STT-RAM is a preeminent solution for embedded flash and embedded SRAM, and for new market application as well, such as AI, IoT, where the low power and persistence are critical. On top, IERAM is extensively explored lately as analog memory for machine learning and neural network applications. Next. Let's look into different emerging memory technologies through this table. All the emerging memory listed here are exploring new material as memory element compared to traditional silicon charge-based memory, and cell architecture as well. Selector is a key device to enable stackable cross-point architecture as shown in 3D XPoint for high density and capacity for both embedded and standalone memory application. STT-MRAM is using electron spin instead of electron charge and deliver high speed, low power, virtually unlimited endurance a leading candidate for embedded memory solution, also could potentially replace DRAM, storage class memory with 3D structure with a selector. For both ferro and nanotube RAM are still in research and development stage. Two versions IRAM listed here is oxygen vacancy and dissolved metal as a conducting bridge. They are very promising for AR application. The key challenge for IRAM for AR application is to increase write speed faster than 100 nanoseconds. The PCRAM is now very successfully implemented in 3D cast point storage class memory, as I mentioned. Next, please. Here I explore a little bit in detail on SCCRAM I'm working on since a long time. SCCRAM show a very competitive advantage over other emerging non-volatile memory for edge application, namely high speed is very comparable to last level cache, zero standby power, higher gigabit density capable, virtually unlimited endurance, highly scalable down to 0x nanometer. So it's ideal solution for edge AI application, such as transfer learning and inference processing. Next, please. Let me summarize my talk by looking back at the two groundbreaking memory in production in last decades. I would like to emphasize that 3D technology play a leading role, and of course, new material, new device, and new process enabled 3D stack realization in standalone memory. We will continue this 3D direction even in a broader sense. Meanwhile, to continue memory scaling, we need also more cross-domain innovation from new material, device concept, leading edge manufacturing process, system design, all the way to advanced 3D packaging, including heterogeneous integration. Finally, I think strong ecosystem collaboration from chip system designer, manufacturing fab, tool and metrology vendors, IP provider, and downstreaming advanced packaging is very critical to keep future memory scaling. Thank you.
Thank you, Dr. Bai. Ladies and gentlemen, I do not see too many questions and answers in the box. Right now I have two, all right? And I think I'll give Professor Thean some time to go through these questions and some of the other questions. Please feel free to ask Dr. Hui on some of the MRAM issues, like what the MTJ stack process issues to any of those 3D interconnect development work in iMac for Dr. Lauer, or even whatever brand of whiskey Kelvin likes to drink right now. Please feel free to ask in the Q&A. Of course, Prof. Thean will be choosing the right questions to be addressed to all the different panelists. All right, so Prof. Thean, you want to take over, or should I read off some of the questions?
Well, yeah, I can. Okay, let me maybe start with some of the groundwork questions, right? I mean, which was asked in the beginning, and we'll go through some of the questions and you can bounce those questions off me too. Okay. I think one of the things that maybe we should start is to ask that recurring question again, right? When will Moore's law end? So I think the question is, will Moore's law continue to be going strong for the next 5 to 10 years, right? Just to put it in perspective, in 5 years' time, we're talking about 1 nanometer or 2, and then in 10 years' time, we are going to be talking about sub 1 nanometer. So that's 0.7 nanometers or 700 picometers, okay, in terms of technology generation. So I would ask Loader to see if he has any views on this.
You mean, by nature, we believe that what you saw, the roadmap that we've shown there, gives us at least for another decade challenging work, where you will have dimensional improvements, because whatever device we put out there, whatever pitch we put out there, there is underneath a lot of material changes in order to realize that, and still there are quite some opportunities. Like if you see but it's years of work, right? In the interconnect, we bring in various new metals, binary metals, hybrid techniques. So a lot of things come in order, and they do enable the dimensional scaling. So in a sense, the Moore's law continues even for a part at that level, but as I told it also, it is to be seen in complement with DTCO and STCO, right? The combination that you will have, economically speaking also, right? So you will not just do a new technology node for a 10% improvement. So it will be the combination of having specific material improvements, and introducing a new material in a fab or in a module is something that you need to be very confident about. So you need to have a lot of data before companies want to do that. So, and there has to be a significant improvement. So in top, you need to be able to show there is this improvement, and then you want to show it also combined with the right possible, what does the designer see in terms of improved libraries, or so what system can he make? Just, I expect this is the change with the future. We will need to explain this technology will serve this design solution better, or this technology will serve this system better, so that people know why they invest, not just investing for tons and tons of money for a percentage left and right. No one will do that. So you will need to have the catch from what is the benefit when you look at it from a design perspective.
Okay, that's good. So any other panelists would like to add to this question? Where do you see? Yeah, go ahead.
Yeah. I do also agree. I think Moore's law ending or scaling, I think it's all relative, right? We're talking about new device architecture. Does this labeling of 2 nanometer, 3 nanometer make sense anymore, right? I think a lot of, and as you know, some of us go back a long way. There's also a marketing element in this, right? But perhaps the metric that we should be looking at needs to change, right? Productivity of a design. You talk about TOPS, for example, right? This is an important metric. How do you combine a design metric and a process metric, or process technology metric is something to maybe we want to consider, right? If you couple that with a system metric, that's even more complicated, right? So not trying to solve the problem here, but maybe generating more questions for us to think about, because I think nanometers does not make too much sense these days, because it's becoming a bit vague what that actually means, right? The number, right?
It's true. I think when I was working on 32 nanometer or 28, I think I thought the 22 nanometer team is doomed. There's no scaling past that. Boy, was I wrong. That's the funny thing. Okay. Well, if I'm gonna start taking questions from the Q&A, there are quite a few people that have asked, right? So I'm gonna take the first one. So there's a question about memory computing, in-memory computing. What are the key challenges for in-memory computing? Any takers? Maybe Yiming?
Unmute. Sounds.
For enabling in-memory computing, first of all, you need a very high performance memory. and unlimited endurance and low power consumption, and also very scalable. This technology should be to like 0x nanometer. So on this end, I think I mentioned STT-RAM is very promising for in-memory computing at the edge, and because of the lack of very high capacity STT-RAM. But otherwise, STT-RAM deliver a very good attributes for the memory computing in the edge device.
Okay. I like to also add in-memory computing. I think one of the as what Dr. Huai has mentioned, there are a lot of research going into analog memory. So there are a lot of opportunity to basically do in-memory computing with analog memory because you can represent real floating point numbers. The issue there is variability, and obviously RM doesn't have the same high endurance capability as MRAM does. So there are these are topics that are still currently in hard research. But in-memory computing is also largely an architectural question. How do you represent the problem such that much of it can be solved using memory devices? Okay.
Thanks, Project. Can I make a note to some of the participants who are writing through the webinar chat? Please address all your questions to the Q&A box you see at the bottom. Please use the Q&A box. Oh, there is a question from one of the participants who I know is Dr. Lai. Dr. Lai is a director in Applied Materials, focusing a lot on thin film CVD. He has asked a question about 450 millimeter wafer size. Is it no longer the driver for productivity improvement? That's a question that I've also been asking. Some companies have tried over the years, and there was some paper on record to start 450 millimeter. But do you agree that it's no longer the driver for productivity improvement? Or should we stay with 300 millimeters or even 200 millimeter wafer size and just focus on the size of devices for productivity?
So yeah, okay. I'm going to attempt to answer the question, even though I'm an academic now, right? Putting my hat back on, my old hat from the industry. I think the 450 discussion. Okay, for folks on the line that are not familiar, obviously, much of the wafers today are on 12-inch, 300 millimeter. And of course, a while back ago, people thought, well, if you're going to make it cheaper, the cost of per die cheaper, you can go to 450 millimeter, which is a bigger wafer size. And obviously, there was a big effort in the industry to bring the tool infrastructure to do this. So there was a big effort at Semitech in New York. There was also an effort starting in IMEC in Belgium. Now, the issue is, ultimately, I believe the challenge to 450 is still to do with a market. There are too few players out there to create equipment for 450. And that didn't create the right sort of business model to support it. I know that all the top fabs, Intel, TSMC probably were asking for 450. So I think it's still a possible path, but the question is, we need to get the business model right. That's it. The technology, I think we have it. I think scaling it up. I think the technology that went to EUV, for instance, is just enormously complicated, right? And scaling it up to 450, my feeling is that it's probably within the capability of the companies to do so. The question is, do we have the business will to do it?
Maybe I would like to add to Aaron to that. Like we were together a few years in a project. IMEC also was investigating, do we need to help or think on 450 and so on. But it's hugely challenging, and everyone was looking at each other to see like who wants to invest and to pay for it, because it's a huge development cost, and indeed a number of companies have invested. But the economical benefit at first sight was at that time not present, right? And so people say, right, if it were available, maybe I would consider, but no one was saying, okay, I'm opening my wallet to put so much money on the table to it all happen and to develop all the new equipment. And so I think that's when the project got archived. Also, I have this impression everyone will like to improve. If there is nothing else to improve, maybe people will have a look at it. But if you see what's out there, there are a lot of new things that people will probably see more improvement, and you will not do everything together. If you take the litho, Aaron was referring to it, like the challenge to make it on 450 in terms of forces and so will be huge because it's a stepper system. So in order to do that on these wafers is a huge development. While today you see we have been making progress with EUV, and then now the focus is on bringing high-NA on the market. And with EUV and high-NA EUV, I think there is more benefit to be realized in the overall industry system than introducing 450 on short term.
So I guess it's really two parts, right? We have not milked enough from the 300 millimeter, and also the ecosystem for 450 millimeters is not there yet to make it productive. So it's too fast, right?
Yeah. I think economically is not viable, and so you can see that in TSMC, and they build a 5 nanometer and a 3 nanometer fab. They already planned is 300 millimeter. So this will not happen 400 millimeter for in the near future. Yeah,
that's true. There is another participant whom I know has got interesting question, but it's on gallium nitride power applications.
Yeah. So is it from IMEC?
Yeah, you know, he used to be from IMEC. He's Yoganan, Dr. Saripali. Right?
Yeah, I saw the question come in, but it disappeared from my. So actually, I'd like to address that question. You know, I think, and then I think probably Kelvin would like to say some words too. I mean, it relates to heterogeneous integration. I think. One of the interesting thing about, you know, people are starting to look at, can they bring compound semiconductor into on chip for some heterogeneous application? And the question is for what purpose? And in terms of gallium nitride, I think, you know, a lot of the power management I see today is off chip, and the main chip itself has more and more power domains that need to be managed. And so having, you know, power management ICs that are much more closely integrated on chip becomes very interesting. So in that respect, you know, even the integration of gallium nitride based technology, which on the same die as silicon, can become interesting. Now, how to do it? I mean, you know, they're definitely stacking technique. But on top of that, I think the other very interesting part will be in gallium nitride plays a strong role in power amplifiers for RF. So, you know, in order to reduce the latency for next generation communication chips, you have to put the compute and the comms front end and RF front end closer and closer together. I think that's another opportunity where gallium nitride can play an enabling role if you can all using chiplet technology to be all placed onto the same interposer, for instance. So these are some of my thoughts on that particular question. I think Kelvin, I think on custom silicon, I think you spoke briefly about this ability to bring in different reuse of IP and even different type of functionality chips together, right? I think this also falls into that category in terms of enabling technology.
That's precisely right. I mean, when I talk about time to market, I think for product companies, time to market could be everything, right? The faster you introduce products in the market, the larger the market share you will gain, right? So reusability is a very key word these days. So chiplet, I think it's not new. Many companies have been talking about that. But the deployment of chiplets is a lot more evident these days, right? And I also expect that a wider deployment of chiplets can be achieved if there are more standardization, especially between the different chiplets, right? What kind of interfaces? Is there an industry standard that governs the interface requirements, for example, right? So gallium nitride is just one, because you precisely talk about the power amplifier function. If one can design the system such that you can bring the functionality closer together, the net level PPA gain could be really interesting, right? And this is actually what matters to the system developers, not so much the SoC or the single silicon PPA, but it's the system level PPA, right?
Yep. Any panelists like to add? If not, we can move on to another question I see on the Q&A board, which is quite interesting. It says, here, I think it's from Clarice, which asks, what are the chances of recycling silicon in future fabrication? and in terms of what considering it comes to picking a material. Anybody have any thoughts on this? This is a sustainability question for electronics.
No.
Interesting question.
Interesting.
I'm going to attempt. I think one of the interesting thing is in IC manufacturing is that we use a lot of rare earth type of highly precious metal. I think Loda was talking about interconnect technology. Interconnect technology moved, for instance, the local interconnect moved from tungsten to cobalt, and then potentially to ruthenium, which is super expensive. I think so. If there are ways to recover some of these, it's actually quite useful. I mean, even magnetic materials are very expensive. So now, I think silicon itself won't get recovered, but I think the question is how to reuse, precious, rare earth and precious metal. That's an interesting thing from a chemistry point of view. How do you refine it and get it back? That may be interesting.
I would like to add to Aaron's comment also we see an increasing interest in sustainability of what you propose in terms of future solutions. And actually it has become a special project in IMEC we started it and we will do it for another few years, to assess and try to model all these elements, like what is the cost of certain, not per se just the process cost like we always do it, right? The C in PPAC or something, but the cost in terms of sustainability and all these things, and how do you deal with that? So we are looking into that and we hope to come up with some better assessment. Today, I cannot say whether silicon recycling is part of it. I really cannot judge, but like Aaron is saying, metals or water, all these things we need to look like what is the cost of that. We are doing that, so probably we come out with more results like next year or so. Yep.
Okay. There's another question about MTJ. I think this is for Dr. Huai. I think the question is, MTJ is capable for multi-level charging, multi-level programming. Can it serve as analog memory? Any thoughts?
Oh yes, I think for the they have two paths for the computing memory. Of course, people use analog memory such as RAM and intensively explore. But on the other hand, people using binary to just need more capacity to achieve the same function. So for STRAM, I mentioned that for all the emerging memory technology, in order to have a very high density, high speed, and the 3D cost point is a direction to go. And all the focus is on how to develop a selector, a novel selector, which can cope very well for the memory system requirement. And that is, I think, the key challenge now, and also very intensive research on the emerging memory technology.
Yes, thanks, Dr. Huai.
Thanks, Dr.
Yeah, so go ahead.
are we ready for packaging questions? Because I think we've got a couple.
Yeah. So let me see.
Zhu Zhendong was asking about package technology development, and Mr. Ding from TFAMD is asking about a prospect of 2.5D compared with wafer level fan out on substrate.
Yeah. So okay. Let me ask the question on the prospect for 2.5D package compared to wafer level fan out, right? Substrate. I think Kelvin has talked about chiplet integration, and one of the approach to chiplet integration is obviously system on an interposer technology, and even that there are several ways to do it. So obviously, I think there are many aspects of packaging innovation. I think 3D, the cost, not all applications are suitable for 3D, complete 3D stacking. 2.5D becomes very interesting in terms of enabling heterogeneous systems. Now, there are other aspects of packaging issue, for instance, reliability on back end of line and all that, but I'll leave it for later discussion. But I think at least for now, the views on 2.5D package, I think I'll open it to the other panelists to take a crack at that also. Maybe start with Kelvin.
Yeah. Okay. So for 2.5D, I don't see as competing or replacing. I think both will coexist, right? Because the application space is so different, number one, right? 2.5D, if I can cite a couple of examples, a lot of products are actually already being deployed today, right? Having, let's say, FPGA together with high bandwidth memory, for example, or even logic chip with high bandwidth memory, they're all deployed in 2.5D, silicon interposers. It is true, silicon interposer is expensive. So there are a lot of effort, research to try to, for example, replace silicon interposers with organic interposer, for example, to reduce the cost, right? But to serve very similar applications, very large die, very high bandwidth demanding type of applications. For fan out, less demanding, more suited towards a consumer mobile type of space, and that's also being deployed in very high volume environment today. Yeah, so I think both will be needed. It's just very different application space.
Yeah. So related to this question, I mean, do you see traditional foundry getting more and more into the packaging space because of wafer level fan out or 2.5D? Versus traditional that,
and that's a great question, right? I think, well, not I think, but it is already clear. I would say the large foundries like TSMC or Samsung Foundry are already building out more in-house capacity when it comes to packaging. It's very evident to them and obvious to them they are able to, I would say, extract more value and provide more value if they can tie packaging, a very advanced packaging, back to silicon technologies, right, to provide a total solution. So yes, foundries will continue to scale out packaging, I would say, capabilities, not only research, but in high volume environment. That can also disrupt maybe the overall OSAT landscape. Will be interesting to see.
Yep. Thanks.
I would also like to align with Kelvin to say many things will coexist. I think all this packaging in 3D, it's a palette of technologies that is available, and there is a lot of improvements going on each part. You will see it's very application dependent what will finally be chosen, but probably they all come somewhere in certain areas.
Yeah. I would also echo this point. In the memory hierarchy, there's also a gap between the SRAM and DRAM, and in one approach also using this 2.5 interposed packaging is high bandwidth memory 4 and graphic DDR6, which can be fill the gap and with a very high bandwidth. And as I mentioned, in other hand is monolithic integration is using SDRAM, but the capacity is limited, and 1 gig, maybe 2 gig. But using this packaging, and people can really fill this gap with a huge capacity. memory capacity.
Yeah, indeed. I think having all this packaging, advanced packaging options actually is very nice, because we all allow us to optimize the power, performance, area, cost, which is very important for different type of products. And I think this is where, in fact, having the coexistence of different approaches is a good thing. Yeah.
Yes.
So I see a question on the Q&A board. Questions on integration of 2D materials for next generation technology. Is there a wafer scale transfer technology enabled? And it says here, IMEC is pushing hard on wafer scale transfer, but we still look like far away from reality. Okay, so
yeah, I think so.
yes, Loda, you have no choice. You have to address this.
Yes, I know, but I'm not so sure whether it's one of the techniques, and we're at a stage that we can investigate the various ways of either wafer scale transfer or deposit or whatever. So the point is, we are at the stage that this is where we will need crucial disruptive innovations. We were recently doing some brainstormings, and we thought, okay, maybe the enablement of 2D materials might be something like years ago, people were dealing with IK, right? You are facing a bottleneck, and then you need a disruptive innovation that brings you again forward. So if we're able, so this will require huge collaboration also with the key suppliers to work on the fundamental process steps to make sure how to do that. This will require a lot of R&D also at the characterization, measurement, a lot of things we will need to study there, modeling, to make sure that to enable that. Otherwise, it will remain an exercise in R&D level, which is not the purpose.
Yeah, I agree with Lo. For this kind of like cell assembly, two-dimensional material is really require huge, intensive research and development. And I mentioned this in the memory hierarchy, one called molecular memory, which is also like 2D self-assembly material, can be glued on the like access device and layer by layers. But this kind of research is really needed a huge budget. I fully agree with Lord. In the future, memory and silicon, research and development, and the huge effort, and from all the aspects, from material, metrology, and characterization, and so on. Yeah.
Yep. And I'd like to add one point, which is also the part of embedded in the question that was asked, is that how ready are these technology, right? So the assumption is always that these 2D materials need to be high quality, and sometimes that may not need to be. So it depends on what the application is. I think the technology, the way we manage materials and use them has advanced quite a lot. Just to give you an example, right? So when I think back in the early 2000s, we were trying to put high K metal gate into the process, and high K itself is a metal oxide. It's unstable. It has defects and stuff. But today we use it routinely as your gate dielectric. I mean, who would have thought that you replace thermal silicon dioxide on that? I think the key is, how do you manage the material? How do you manage the defects? And so I think those technology will come as time as we continue to study and investigate and develop solutions for these type of problems, right? But the general trend is true, which is that as what also Loda and Dr. White has said, I think there are a lot of memory technology that are required that will require material innovation. There are a lot of motivation to put functionality in the backend. That means move devices, active devices, in the backend and interconnect so that we can do reconfigurable logic, reconfigurable memory, and stuff like that, right? And so these devices all require low thermal budget type of processing and materials. So you have options that's why there's motivation to develop this kind of new materials for this application, right? If you cannot do it at low temperature, you will do it through interposer technology or 3D stack. Okay.
Yeah,
Anybody else?
I think yes, like a 3D DRAM, people try to put all the logic circuit underneath the array, but in this end, the selector device on the array needs a lower thermal budget. Otherwise, you will destroy the logic part of the underneath. So that is true. But I think the 3D DRAM is very close, probably, and I think IMEC also involved. I think in this research, I read a lot of papers, and yeah.
Yeah, and the possibility also, that's where I mentioned IGZO, right? The IGZO material that would enable a transistor that you could put as an periphery under array and at a low temperature. So these are all possible scenarios.
Mm-hmm.
Okay. Okay.
I think we have time for maybe 2 more questions.
2 more questions?
Or 1 more? Or I think there's only 1 more question that left to be addressed. I think
so,
it's a good, interesting question.
Yeah. So yeah, this is an interesting question. So there's a growing trend that software companies are designing their own chips. Okay, I think we all know who they are: Amazon, Facebook, Apple, right?
Google.
So, what are the pros and cons, in terms of challenges the industry will face with this kind of trend? Anybody want to take this question among the?
Well, I probably will take the first attempt at
Yes, Kelvin, go ahead.
Well, they're software, they are services company, they're also hardware companies, just to expand on the question, right? Why are they doing this? The pros and cons. The pros, I guess, for these companies is they are starting to see an advantage to have more custom silicon when you say designing their own chips, because they're able to optimize the stack, meaning the silicon performs the functions that they require. Let's use Apple for the sake of discussion, right? I mean, the apps that they are running is all highly integrated with their actually SoC architecture. How they design the CPU or the GPU, for example, is all tied to the app, right? Or the just to simplify the illustration, right? So highly optimized, and then in the case when it's highly optimized, you do reduce costs as well, because you remove unwanted functions if you purchase off the shelf, let's say ASSP, right? The challenge is, of course, how can you build a team to do this, right? It's not a 1-man team, 10-man team. It takes years, right? If you look at the history of how Apple managed to build up this capability, they acquired a number of companies, right? They learned through working with partners, and eventually they are self-sufficient, right?
Yeah.
It's almost back to the future, right? You're starting to see the vertical integration coming back, not IDM per se, vertical integration coming back, the know-how and all that. Yeah.
Actually,
very interesting.
I would like to add also to that. It's kind of, this is what I mentioned earlier, the STCO, right? System Technology Optimization. If that is true, then this is what you would expect to see. That from you think from a system perspective, you think you may be benefiting from kind of tuned solutions for your type of applications, for your type of architectures. And that's so how successful that will be, so we need to see. But what our expectation is that probably you may have tuned preferences, right? For different architectures may at the end of the day benefit from different technology choices underneath.
Interesting. So would you guys think at one point that they don't only design their own chip, but they want to build it also using their own fab?
This is unlikely.
Well, I will always argue never say never, right? So perhaps maybe not a logic fab, maybe something more targeted first, a display fab, for example, that they see that maybe it's of high value. Allow them to allow a company to differentiate themselves against a competitor, right?
Yeah.
We listed Amazon, Facebook, Apple. These are very large companies, right? So there are not many of such companies in China. Obviously, there's also the BAT, right? The Baidu, Alibaba, and Tencent.
Yes.
But
Yeah.
not many. Yeah. I just want to bring maybe another dimension. This doesn't mean smaller companies cannot enjoy that, right? This is why I mentioned the rise of custom silicon. If you look at the trend of design services company, it goes up and down, right? But there is again an increased trend of more design services company coming back. Why so, right? Because OEMs and system makers have huge appetite now. They do not want to build an internal team as yet. So instead of having an internal team, they outsource. So they outsource to multiple design services company to try to accomplish somewhat an equal effect, right, of getting custom silicon. So that is a trend to watch out.
To add to that, actually, I know of a certain foundry that is actually starting to develop their own hardware because they are facing issues with leading tech nodes from edge equipment to even some of the EUVs, right? I mean, they're not going to create equipment from scratch, but they're starting to build some hardware development teams to do modifications, they can customize some of those equipments for their processes. Because you know, certain equipment manufacturers, it's hard to do customized equipment for specific fab process with their own PDKs, right?
Yes, I think that's interesting. In fact, you know, whenever a supply chain or part of a supply chain is threatened, usually that happens. And so it depends on how big you are to make sure that the supply chain is open. I think the interesting question would be at some point would be to look at China. I think that would be interesting.
It's a little different model now. Yeah.
Yes.
Well, if we go beyond technical reasons, if we go to political reasons, there are many other reasons of technology challenges, right? Yeah. Well, I think we have covered most questions. Are there any topics or anything that Prof. Thean you want to summarize before I wrap up our webinar? I think go ahead.
Yeah, so first I'm having fun. I mean, I'm definitely we touch on some very, very important questions. In fact, that's actually out there in state of the art questions, right? So it's also a great opportunity for me to touch base with all my colleagues and the experts in the field on this. I think that I want to thank everybody for that opportunity and great questions asked. I think right on the dot. So I think, you know, I hope to see that this type of forum continues. Right. Yeah.
We do plan to have it on a 6-monthly basis. And of course, if you want to have more fun, you have more regularly, just let me know. And we will be hosting post webinar surveys. We'll be sharing some of the summary of what we have shared today on our LinkedIn portal, so that everybody can have access, or those who have missed it can have an overview of what we have shared. And then, of course, we'll hook up with any questions from the participants who are too shy to even send it on text. If they've got any questions, they can direct to us, and we'll get it to you guys directly. All right. Yeah. I think like what Prof. Thean said is really fun. I think this is really a start of something that we can do on a more regular basis to generate more interactions within different communities in different time zones. Right. So without much further ado, I know it's getting really late for those in Asia. For those, for Dr. Huai, please get a cup of coffee.
It's so fun. That's great webinar. I think everyone, I think all the speaker probably echoed all the is like the 3D direction and new material and the cross-domain the innovations and the ecosystem collaboration, and I think great webinar. Yeah.
Yeah, the point is also we cannot cover what research and the whole semiconductor supply chain is so hard, so wide, right? It's hard to cover all different topics in 90 minutes. But what it at least cover is to generate interest for future webinars we addressed.
Yeah.
And we can also create some social media links whereby you can have access to some of the participants to address get large. I think this is what we are also trying to achieve. So to all participants, thank you for staying up. And we will be sending out all the webinar surveys or any questions you want to direct to any of this, our esteemed panelists. We'll be more than glad to facilitate. Well, to our, I would like to thank SpenglerFox for helping to co-partner in hosting this webinar. Without them, it would not be successful as well. Thanks to Jacques, Dimitri, Josiah, who's working in the background, Peter Zabo, and I'm sorry if I've missed any names out. Thank you, everyone. Thank you, Prof. Thean, for graciously moderating this crew. And thanks, Kelvin, Dr. Lowers, and Dr. Huai. It's really my pleasure to have you guys on this panel. I look forward to having you guys again on this panel, and see you guys soon. Thank you, everyone.
Okay.
Thank you.
Hey, thank you all of you.
See you guys again.
Thank you.
Thank you.